Let's begin. Welcome again for another week of CFD. So this is the third week, and we've been pushing the boundary of knowledge, I hope, for what you know. You might have seen these things before. Hopefully you're seeing them in a different light. And if you've observed, my approach is very hands-on. We're going to collect information. We're applying the simplest finite difference schemes to these equations and seeing what happens. When we applied the central scheme on the diffusion equation, we recognize that for certain time steps, the solution becomes unstable. We're going to do the same with the advection equation today. But I will first start by, I put a couple of slides to describe to you the stencil operation that I did last time in class. I know most of you ended up figuring that out, but I figured a diagram will help you anchor that idea in your mind. So if suppose we have this sort of grid, just a bunch of points in 1D, and we have these values for the dependent variable u, put in some bunch of numbers, 1.1, 2.3, just to put in some numbers, okay? I'm going to exclude boundary points in all stencil operations because the boundary points are usually not a degree of freedom. They're either specified by the user, well, they're specified by the user or periodic, right? And so really you have no control over the boundary condition. It's set separately. So we treat the interior only, and then we apply the boundary conditions separately. That's what we've done with the diffusion equation, where we had knowledge of the endpoints. Okay, so we'll be focusing on the interior points from 2.6, the interior numbers. And now suppose you wanted to compute a derivative using backward differencing. So this procedure applies to any stencil operator. You just have to reason about the logic, the way I'm going to do here, and then you'll figure out what the array slicing needs to look like. So suppose now you're doing a backward differencing operation. And again, we're applying this only to interior points. So we're going to start at this point and then this point all the way here. So at this point, this is going to say this is 2.3 minus 1.1 over delta x. At this point, it's 5.1 minus 2.3, and so on, right? So this is just a backward differencing formula. OK, so this is what this would look like. Again, I said the boundary conditions are not affected by this, OK? So we're not looking at the boundary conditions here. So for the first point, you're combining these two, 2.3 minus 1.1 over delta x, right? That's the backward difference formula. ui minus ui minus 1 over delta x, agreed? So notice now I'm going to have two colored arrows, one green and one to be 5.1, 2.3 over delta x, so forth, right? 7.6 minus 5.1, 4.2 minus 7.6, 3.3, et cetera, okay? Now notice that the result consists of the difference between two arrays. The array of numbers that correspond to the green arrows minus the array of numbers that correspond to the red arrows. Agreed? So if you were to take all the green numbers, that would be 2.3, 5.1, 7.6, 4.2, 3.3, 2.6, minus the array of the red numbers, 1.1, et cetera, you will get this result. And divide by delta x, you're going to get this result. So if you think about it, you get all the green numbers in this array, and that's only a view of the full array up there, which is u of 1 to minus 1. So it gives you this subset of numbers, right? The numbers that correspond to the red arrows are, you're going to start from 1.1 all the way to 3.3, right? Now, when you take the difference of the two, what do you get? You get 2.3 minus 1.1, 5.1 minus 2.3, 7.6 minus 5.1, 4.2, and so on. And that's how I built that stencil last time, okay? Very simple. So you can apply this to any stencil operator, whether it's a central scheme, whether it's forward difference, backward difference. Use this kind of logic to vectorize the operation. So Adnan reminded me last time that, yes, this is indeed vectorization. Internally, Python is going to loop over these arrays and take the difference. But that loop is more effective than any loop we would write, because it's part of the compiled Python code, okay? I don't know why I have a second array here. Okay, so we'll skip a slide. Okay, and perfect. So now, remember last time we finished off with the unsteady diffusion equation. We did the central scheme. We derived the condition for stability as the Fourier number less than 0.5 in one dimension, okay? And now it's time to turn our attention to the advection equation. The advection diffusion equation consists of advection and diffusion. We started with diffusion because it was a little easier. We're going to do advection right now. Okay. And advection is simply the ability of a fluid flow or a flow to move things, to move information along with the velocity. We start with the simplest example, which is in one-dimensional unsteady advection in a periodic domain with the forward in time, central in space scheme. Okay. So why a periodic domain? Because advection is moving things along space, and I wanted to move it to infinity. So if there's no decay, if there's no forces fighting advection, the advection equation tells you that you can move information to infinity. So I'm going to put a periodic domain. It's like you're spinning around the Earth. You keep spinning and spinning, spinning, right? There's no end. That's what a periodic domain would mean. And I will use the forward in time, central in space scheme. Why? Because that's the simplest one, guys, right? Forward in time is that simple forward derivative. It gives us the ability to compute things explicitly. So it's an algebraic operation. It's an explicit scheme. Central in space, that's a second order scheme, so it gives us good accuracy. Central, it's well balanced between the points to the left and the points to the right. Okay, so this is the advection equation. It's a balance between a time derivative and a spatial derivative. And the way I like to interpret this is that advection is only a result of a frame of reference change from a Lagrangian perspective to an Eulerian perspective. There's no concept of advection in a Lagrangian particle, right? Because it is moving with time, okay? So, but once you do this, you pay the price with what we perceive as advection. What this is saying is, I'm going to take this quantity u, starting with the initial condition. So the true solution to this equation would be to take this initial condition, u0 at x, could be a Gaussian, could be a sine wave, whatever, and just move it. Just advect it. I'm just going to move it in space, okay? So that's why there's and there's a balance between space and time. There's the same thing for advection because they come from the Lagrangian Eulerian description, right? Time and space are essentially the same thing in this case. And so you're just translating things in space. As time evolves, you're translating things in space. So if you were a particle riding on that curve, you see nothing, right? You're just moving in time, right? There's no perception of space. Typically, so this minus sign tells us that if c is positive, things are going to move from left to right. And if c is negative, things are going to move from right to left if your x-axis is from left to right positive, okay? All right, so you've probably seen this in your ODE or EDE course. What we're going to do is take the equation, apply point I, time level, okay? And then we will approximate the time derivative with forward Euler approximation, which is un plus 1 un at delta over delta t point I. And then the spatial derivative, we said we're going to do a central difference scheme on the spatial derivative. Now, this is a first derivative, not a second derivative. For diffusion, the second derivative had a 3-point stencil, I minus 1, I, and I plus 1. In this case, this is a first derivative. The stencil is going to be minus 1 and 1, right? So it's going to take a balanced approach between I minus 1 and I plus 1 over 2 delta x. So that's the difference between the two neighboring points. So when you do this diagram that I like to show, what this is showing is that the new value in time, as we move in time, the new value of the information of the dependent variable is going to be equal to the old value minus this number, c delta t over 2 delta x, after you combine things, times this difference, all right? So in this diagram, ui at n plus 1 is taking information from the past at these 3 points. ui minus 1, ui, and ui plus 1, right? So you have ui, ui plus 1, ui minus 1, similar to diffusion, okay? Okay, now we have an issue with periodicity, and the way I like to implement, there are a few ways to implement periodicity. The one that I found to be the most convenient and that will set the stage up for when we do Newman conditions and more complex boundary conditions with the staggered grid is going to look like this. So typically, you would have an array. I'm indexing here from 1 for simplicity. So you'd have, this is the boundary point, and this is a boundary point. If periodicity is satisfied, this entire grid will be repeated over here. So this un would be the same as u1, and u1 would be the same as un. And you would repeat over and over again. So how do you implement this numerically? You don't have information. So you need to compute un and u1, and then you need to make them equal. Right? So how do you do that? Here's a little beautiful trick. So in practice, you will have an array, U, that contains the solution variables. Instead of creating an array of size n for the solution, you add two fictitious points, one point on each side of the grid. Okay? We call those ghost points, right? So thank you. So we create an array of size n plus 2. So there's the n interior points, but we add one point to the left and one point to the right. We call those ghost points or ghost cells, one on the left and one on the right. And those are entirely fictitious. They are just for the sake of doing the numerical implementation to simplify our lives without having to worry about what we need to do at these boundary points. And here's how periodicity works. What you would do, you would take the value. Remember, you're solving quantities over here, right? You're solving for U2, you're solving for U3. Once you're done with the calculation, you take the value of U2 and plug it in here. So now you have a value in the ghost cell, so you can compute UN. Okay? So you come to UN, you compute it as if you're just doing the advection equation. You compute, you advance in time, but you have a value here. So your stencil is valid, right? When you're doing, at this point, when you're doing I plus 1 minus I over 2 delta x for the advection term, you have information here because you inherited that from U2. And then you also do UN minus 1, you move the information to this point so that you can compute U1 as if it's not a boundary, rather as if it's part of your degrees of freedom. But when you inherit information this way, you can show that the solution at U1 and UN will obey periodicity. Okay? The trick is, so you start your initial condition, you initialize your initial condition at the interior points, and then you apply periodic conditions. So you have information at these ghost points. And then you just go apply the formula at all the interior points from U1 and UN. And I know these are the boundary points, but because of periodicity, we're just going to treat them as they're part of the solution process. Why can we do that? Because I have information in the ghost cell that will make these points valid, as if I'm applying periodic boundary conditions. This will be valid in the future when we're going to apply Dirichlet, and in human conditions, you will see we'll set values in the ghost cells and just apply our formula everywhere, including the boundary points. Okay? So when you do this, you say, if you have your array of size n plus 2, then U0, which is this point, is equal to U minus 3. So minus 1, minus 2, minus 3. Right? So you take this point and put it here. And U minus 1, which is this guy, is equal to U2, which is this guy. Okay? Now, I asked GPT to drawings. Okay? This is the cell of a ghost. So a ghost, what does a blood cell for a ghost look like? And then this is a ghost cell where, a ghost is sitting in a prison cell. That's pretty neat, okay? And by the way, ghosts are real, so, anyway, that's a discussion for another. All right, so they become very handy for human conditions, okay? And the finite volume method when we do standards, all right? Let's get our notebooks and Pythonify this equation, okay? So create a new notebook. We'll do this together. All right, so zoom in a little bit. So 1D advection equation with FTCS scheme. All right, so I'm going to inherit the formula here. We will work. Again, I'm not typing a lot of math here just for the sake of time. We will solve the advection equation with the FTCS scheme. Duh. begin equation and then end equation. All right, so I grabbed this from my slides. All right, so it's un plus 1 equal to un minus c delta t over 2 delta x times ui plus 1 minus ui minus 1 at time level n. Okay, so let's go ahead and grab our boilerplate. And boilerplate was the same as last time, if you remember. So you can just copy and paste as we move on, or duplicate your notebooks and start new code. And you can reuse the old code, but I say every time write a new code, because every time you write it, it becomes part of your memory and arsenal, so it becomes second nature to you. You will notice that each time I write it in a different way, and that's okay, because you're in a different mood or you're thinking about things differently, right? So it's the multiple dimensions of our personalities, okay? All right, so let's do this for, just like we were doing last time. We will set a number of grid points, and let's say 100 number of grid points, or whatever, 32, whatnot. And L is equal to 5, length of domain. It's periodic, so it's really not going to matter. And then X is my linspace from 0 to L with 100 points. And dx is equal x1 minus x0. Okay. Okay, what should we advect? Let's advect a Gaussian, for example. What do you think? Okay. Define a Gaussian initial condition. So if things are true, are correct, then that Gaussian is just going to move in space from our perspective. It's just going to move in space. So I will declare, do you know about lambdas in Python? Yeah? Okay. So we can define, we're going to take things up a notch. I'm going to define my initial condition as a Python routine that takes an argument. Okay, at least one argument now. And so so that I call it as f of x. And a simple way of doing this is you declare this simple lambda x, and then it would return np dot exponential, and I'm going to do a Gaussian centered at 1 with a standard deviation squared of 0.05. Okay, so this is e to the minus x minus 1 squared over sigma squared, right? So sigma squared is 0.05. And then I can call u0 of x. So if I were to do plt.plot x and u0, of x, you'll understand why I did an underscore in a second. And then I can plot this, okay? And you'll see it's centered at 1, yes?
I'm not familiar with what lambda is.
Yeah, so lambda is, so this is essentially doing this. Define u0 of x, return np dot return all of this, okay? So it's just a shorthand notation for defining a function in one line. You can add multiple arguments to it, so you could do, let's say x1 and a naught. Then that's the center of the Gaussian, for example. So we could do, then you could say that I want to center it at 2, then it will be centered at 2, right? So you can add, and you can add the standard deviation, so s, let's say, so over s squared, okay? And then you could say, okay, my standard deviation, or 0.1 is going to be very 0.2 bigger, 0.5 bigger, okay? So notice how I added more arguments here. It's just a shorthand way of defining simple Python routines that you want to call over and over again, okay? All right, so let's, I don't know, let's just center it at 1 with a 0.25. Okay, this seems reasonable. Agreed? All right, so now the underscore was only temporary because I need to declare my initial condition just as u0 of x1 and 0.25. So now I'm storing all of those values just in an array, u0, okay, for my initial condition. Okay? Okay. And if you want to be, you would do OB, just kind of make them look like blue. Marker size equal 2. So you know that these are just discrete points, okay? All right, can we go to the next cell? Almost.
What does the underscore do under that?
It's just the name, but I use underscores for temporary variables or like internal variables, or like I don't want to call, I still want to call this u0, but I don't want it to be the final u0. My final u0 is this one. So I just add an underscore to distinguish it from this u0. It's just a naming convention. It comes from C++ for internal variables in an object. You just put everything with an underscore as just a transient temporary variable. Okay. Are we in sync? Okay. So maybe I zoom out a little bit since you guys are pretty close here. So, all right. So now let's get into the time advance. I'm going to specify some time step size, whatever, just dt equals 0.01. We're going to come back. We're going to come back to this point later, okay? So this is in seconds, 0.01 seconds. And then t end, I want to take, say, 100 time steps. So notice last time we said, oh, t end is 1 second or 2 seconds, right? I'm just going to do 100 time steps now just to see what happens, okay? Maybe we do 10 time steps. Do 10. Do 100 time steps, all right? Now, it's time to define our wave speed or advection speed, which is c. And we'll say this is 1.0. That's meter per second wave speed, or the speed of the signal as it moves in space. Right? Just like last time, declare a container to store the solution in time. So we're going to call this sol. This is just going to be an empty list. And now declare the solution array containing ghost points. So I'm going to declare u as my solution variable, mp.zeros. I'm going to initialize it with zeros. Before I set the initial condition in it, I'm just going to declare an array of zeros of size n plus 2. So I need 1 point on the left and 1 point on the right. Zoom in for those on YouTube. Okay. So now this contains one additional ghost point on the left-hand side and one on the right-hand side of the domain. The interior points are simply u1 through -1. Agreed? So if I take this slice, u from 1 to -1, that will contain all the interior points. And that is going to be of size n. Agreed? Because that's n points. So the total array is n plus 2. I take 1 to -1 is going to return only n points. And I will initialize this with my u0. Okay? Now apply periodic conditions. Now I promised you that these ghost points are going to contain relevant information for the solution, so I can apply my time advance on every point, even the boundary points. If I put the correct values in the ghost points, then I can apply my formulas on the boundary points and be just fine. Okay, so that I don't have to reason much about the boundary points. Okay, apply periodic conditions, like we said in that slide. U minus 1 or u0, we started with u0, so that's the left-hand side, the left ghost point is going to be equal to u minus 3. So remember, at this step here, the ghost points contain two zeros, or it might be wrong information in them. At this point, I'm taking the ghost cell on the left, and I'm putting good information in it. u minus 3 is part of the initial condition, right? And now for the right-hand side ghost point, u minus 1 is equal to u2. Okay, so again, if you look at my slides, hold on 1 second. I'll bring this over here. If you look at my slides here, I'm taking this point. So initially I initialized all the blue points with good numbers, with the initial condition. Then I took relevant information and put it here in this ghost point, and this u2, and I put it here. Now these ghost points contain good information that would represent a true periodic solution, and that is going to be enough for my stencil. If my stencil was 10 points, I would need like 10 ghost points, right? And I would need to fill them with good information as well. So the same idea applies. Okay, good. So we started with a good solution now, good initial condition. And let's append our initial solution now. Sol.append u. And now it's time to do the loop. While t less than t end, like we did last time, we grab the old solution un is sol minus 1. So that's going to give us the latest in time, the latest solution in time. And we'll create a new solution. U new is np dot zeros like, if you want, un. Okay? So it's just a bunch of zeros. Now it's time to do all the interior points except the ghost cell. I'm not going to touch the ghost cells. So u new from 1 to minus 1. Remember now, u new is of size n plus 2. Okay, so our indexing has to be done correctly. U new from 1 to minus 1 is un, also from 1 to minus 1. So I'm looking here at all the blue points, all of those blue points. I'm just taking all of those blue points, and I'm going to advance them all in time together. Okay. Now, what is the advection equation discretization tell us? It tells us that un plus 1 is un minus c delta t over 2 delta x times this stencil operation. Now, the stencil operation, I will do it using slicing as well. Okay. So here's what we will do. We will do minus c times dt over 2 delta x. Okay, now it's time to do that stencil operation. And it's going to be ui plus 1 minus ui minus 1. All right? So what this looks like is this, u2 minus u minus 2. So when you think about the arrows that I showed you earlier, this is saying that all the ui plus 1 points, if I start with u1, that's the point I'm starting with. I'm not touching the ghost cell. The ghost cell is going to be only used to calculate the solution. So starting at u1, I need these 2 points, right? So this is going to be ui plus 1 for it, ui plus 1 for this, ui plus 1 for this, all the way to this last point. So if I take u2 to the end, it's going to give me this array minus that array. That will give me that stencil operator for the center. Okay? If you're kind of taking a minute for this, go draw the arrows. Okay, like I did in the previous example, a green arrow and a red arrow. You'll get 2 arrays. Those arrays need to be of the same size. All right? Always the way I think about it, like if I am point I need a point to my stencil is plus 1 and minus 1. Okay, so what are all the points to my right over here? So if I'm this point, they're going to start from this one all the way to the end because I'm computing this guy too, right? So I'm going to take all of these points minus all of those points. Okay?
How much do the ghost points depend on the periodicity of the function?
It has nothing to do with the periodicity of the function. The Gaussian is not periodic. Right? But we're saying advection is periodic. The process of advection, not periodic. The process of advection needs to go forever. I cannot put a domain going from 0 to 1 billion meters, right? So I create a small domain and make it periodic as if it's going to be, think of it as it's moving, it's repeating itself. It's spinning around the Earth, right? And so it has nothing to do with the periodicity of the function. It's just the domain we make it periodic so we can look at what happens at a signal as it goes to infinity. So we will see later that this is going to be very useful as we study the upwind scheme, for example. We will see that it's going to diffuse that signal. So yeah, bear with me a minute. We'll see that. Good question. Okay. All right, so that gives us at all the interior points. Now what do? We need to do the same thing for periodic conditions. So we're going to take this. Now we updated the interior points. It's time to seed new information at the ghost points. So I'm going to do u new, nothing. Yep, nothing new here. And then sol.append u new t plus equal delta t to the time advance. All right, I think we're ready. Okay, I got an error. T is not defined. T is equal to 0.0. All right, it's just a timer. Okay, awesome. All right, so we can plot the solution or do the animation. Let me grab my animation here. And we might need to adjust features in the animation every now and then. So let's do every 10 pictures. Excuse me, my Y limit is, because this is Gaussian going from 0 to 1, so I'm going to set my plot limit from like, you don't even have to set the plot limit if you don't want to. So let's see what this looks like. Oh, all right, so let me set the plot limit. It's a Gaussian from 0 to 1. Now when I run it, oh, what is going on? Okay, let's run it for more time steps, maybe like 500 delta t. 500 time steps, let's see what happens. It's expanding, increasing, increasing, increasing. That's weird. That's not advection at all, right? Let's do 10 seconds. See what happens. I have faith in you, solution. It's just going to keep on increasing and increasing and increasing and increasing to infinity. That's not advection. Yeah. Okay, maybe did we make a mistake? Let's try with a different function, guys. Let's do the sine function. Lambda x omega and p dot sine omega times x, right? So maybe we try now with the sine function u0 of x and like 3. Oh, 2 positional arguments, but 3 were given. Oops, not this one. Okay. Okay, so this is a sine wave. Okay, it should advect. Okay, this sine wave should advect, and we'll do our u0 to be u0 is equal to this guy. Okay? Are we in sync? No? Nobody's in sync. Did it crash on you, that Gaussian?
No, I'm behind.
Didn't blow, it didn't grow?
It's stuck.
Pardon me?
It's just stuck.
It's stuck. Okay. So yeah, we'll help around. So it's a very, very sharp. So you're using a very narrow. Square. No. Get rid of the 0.05. Oh, okay. Yeah. Just make it a little bit better. Okay. Okay. So let's see now. Scroll down. Okay. All right. Let's run it. Okay. So scroll to the solution a little bit. Here, you need to add a sol.append u new.
Oh,
yeah.
Of course. Sorry.
Got it? Oh. You can plot it. Try to plot if you don't have the animation script. Just try to plot the last points. Scroll down. This one? Yeah. this here.
What should I solve diffusion?
It should have as many solutions as the,
Yeah, so
that
it
is,
should
yeah.
have more arrays, right?
Yeah.
Yeah.
You're printing UNU, not sol. This UNU is only going to contain n plus 2 points, right? So this will have thousands of, yeah. So you can plot sol minus 1. So if you don't have the animation figured out, that's okay. Just plot sol minus 1 here, just to see what the solution looks like, okay? Plot, plt.plot, x and sol minus 1. Okay, it's going to give an error because it's of size n plus 2. So we're going to go to 1 minus 1, right? This is not a Gaussian advection, okay? This is weird. Something is going on. Let's try the sine function. Okay, so now I'm going to try with the sine function, and I'm going to animate it again. Okay, so let's see what happens to the sine function. I'm going to drop the, okay, so see what happens to the sine function. If you plot it, it just keeps growing to infinity. Something is off, and I don't think it's a bug. Look at that. This is what's happening. But what's happening? It's blowing up. It's not even moving. It's just blowing up. Okay? Do you see that in your solutions? It's still not moving.
It's moving very fast.
Shall play it? No, how many time steps did you do?
I did 400 time steps.
Yeah, did you do some more? Scroll up. See?
Do it for
2.
1,000.
Yeah, so this is wrong here, right? So u semicolon minus 2. Okay. All right. Joel, you got it? Okay. All right. So, do you think I made a mistake? Do you think I made a mistake? I don't think so. Well, I did the mistakes last time I taught the course, so I'm pretty sure I have no mistake in my code. The mistake is in the method itself. So let's see what's going on. Okay. We're done with periodicity. Okay, go cells, etc. So you will find that, actually we didn't try that, but you can try changing the time step size. You can try changing the grid resolution. You will find that regardless of those changes, the solution will always be unstable. The simplest spatial scheme, which is second order accurate, central scheme in space, forward in time, cannot produce a solution as far as we've shown here for the advection equation. Now, is this a symptom of the method, the theory itself, or something we did wrong? Let's see what's going on. Okay, so again, we are going to consider a situation where a single value is being advected on a grid, like we did with the diffusion last time. Remember, with diffusion last time, we said that things cannot go negative, etc. Same thing here. We expect for the diffusion, for the advection equation for a situation like this, we expect for the pulse, or that value of 1, in each time step to move here. So everything is going to move. So in the next time step, this should be 0, everything is 0, this should be 1, and so on. Okay, so let's see what happens in a single time step according to this formula. So if you were to call C delta t over delta x, if you were to call that beta, okay, then, and you rearrange things a little bit, you combine ui, so you have 1 times ui, and then you have a half ui minus 1, and a minus half ui plus 1 times beta. Beta is simply speed times delta t over delta x, and that's actually called the Courant number. What it tells you is, given a spacing delta x between 2 grid points and a speed of a wave, if your choice of delta t will tell you numerically how far along you are moving this signal. C times delta t is speed times time, which is distance, right? So meters per second times second gives you distance. Over distance, it's a measure of how much, relative to delta x, how much your delta t is moving a signal along the grid. Okay? So let's see what happens in a single time step. For the advection equation, we expect things to move. This is because the speed is positive, so things should move from left to right. Okay, so let's see what happens in a single time step. All the points are going to be 0 except for these points over here. So if you were to take this point over here and apply this formula, you get half beta ui minus 1 n. Ui minus 1 n has nothing, 0, right? Plus ui n, which is 0, minus half beta ui plus 1. So you get minus half beta ui plus 1, which is 1. So you get minus half beta, and then you get 1, and then you get half beta. Now you add them together, they're conserved, right? It's still 1. The total value of the signal is still 1. But you have a negative half beta and a positive half beta. There is no value on Earth for beta, a real value for beta, that would not produce a negative value in this grid, which is unphysical. If beta is positive, then this would be positive. Okay, good. But this would be negative. But this is advection. How can you create this? How can you create negative advection for this pulse? It's unphysical. If beta is negative, which shouldn't be because beta, well, let's say speed is negative, right? Then this one becomes positive and this one becomes negative. It's not going to work. There's no solution. In fact, this situation, this scheme, produces an unphysical situation. It's unsolvable. There's no solution for forward in time, central in space for advection. It will always be unstable because it's producing these negative values. That's why they tell you don't use central on advection because of this. Okay? At least this interpretation. We say that the forward in time, central in space, that combination together, you have to have forward in time, central in space together. Combined. If you change time, the formula for time, you will have a different condition. Okay? So FTCS is unconditionally unstable. There's no condition that will make it stable. There's no choice of delta t or delta x or speed that will make it stable. Impossible, unphysical. Okay. In fact, this scheme introduces negative diffusion, which is what is causing these behavior. It's causing things to concentrate and grow, right? That's the opposite of diffusion. It's moving things from low value and increasing the high value. Conservatively, right? But they're just increasing. So you go more negative and more positive, right? You still add them together, you get 1, but you're going to get infinities. You're going to break the bounds, right? So it becomes unbounded. Okay. So to see this, I want to introduce you to the so-called modified equation analysis. Okay. Some of you might have heard of this word. But essentially, the story goes like this. And that's it. It's a very simple idea, and you can apply it to pretty much any linear differential equation, finite difference approximation. So if I were to give you this discrete formula, I was just like, hey, this is a formula. And then I ask you, what equation, what continuous equation do you think this formula solves exactly? Well, you say, well, Dr. Saad, this is the advection equation. Like, yeah. But is it really the advection equation? What happened to the truncation error? When it is true that we deduced this equation from the continuous advection equation, but we truncated things in and when we did the approximation, right? When we approximated the derivative, we truncated a bunch of terms. When we approximated the spatial derivative, we truncated a bunch of terms. So really, this equation, this discrete equation, is equal to the true advection equation plus something else. So it really doesn't solve the advection equation. It solves the advection equation plus a truncation error. Okay, so what do you think would happen if we go after the truncation error? Maybe it will give us some light into, maybe there's one more term here that looks like negative diffusion or that looks like some weird phenomenon, okay? So here's how we do this. You take that discrete equation, okay? And we know that this is our process. It's du by dt equal minus c du by dx. I'm substituting time derivative and primes. So with dots and spatial derivatives with primes and time derivatives with dots, just to simplify because I'm going to have so many indices over here. So this is my governing equation, du by dt equal minus c du by dx, or u dot equal minus c u prime. Now, I know beforehand that I'm going to need the second derivative in time and also the third derivative, etc. But I'm going to stop here because that will be sufficient. So the second derivative, if you were to take this equation and differentiate it in time, you'll get another time derivative here. You do the substitution, you get c squared u double prime, which is the second derivative in space, okay? And the idea for the modified equation, okay, is we go after the truncation error. And here's how we will do this. We're going to take, so we know this, okay? We know this, and that's equal to 0. We're going to take this discrete equation and take each term and rewrite the Taylor series for it around point I and n, okay? So ui at n plus 1 is ui at n plus delta t u dot I at n, so that's du by dt, plus delta t squared over 2 u double dot plus a bunch of other terms. I don't need them because that will be sufficient for me. Now remember what I said about, or actually I'm going to say this right now. For the modified equation analysis to work, you will only need to leave u dot as is, or the first time derivative, because all our differential equations have a first time derivative. They're of the form du by dt equal a bunch of spatial derivatives, right? So you leave u dot as is. However, all the higher derivatives in time, you use the governing equation. So you see this u double dot here. You use the governing equation to convert them to spatial derivatives. So that in the end, our modified equation, or the true equation that we're solving, looks like du by dt equal advection diffusion and a bunch of other things, okay, which are all spatial derivatives. Makes sense? I don't want any derivatives in time higher than second order. I want to convert all of those to space derivatives, and you do this from the this supposed governing equation. So if you were to do this here, this u double dot is c squared u double prime. Okay, so you get delta t squared over 2 u double dot, which is delta t squared over 2 times c squared times u double prime. Okay, so that knocks out the first term. Good. Now let's go after the spatial term, ui plus 1. So ui plus 1, this is in space now, so no worries about second time derivatives. We have ui plus delta x u prime I, which is du by dx, plus delta x squared over 2 factorial, u double prime I plus dot, dot, dot. And I don't need those higher order terms. And we go after ui minus 1, okay, which is that second term up here. So I'm taking each term and expanding it around uin. Uin is already uin, so I don't need to touch it. So ui minus 1 is ui minus, because this is ui minus 1, delta x ui prime plus delta x squared over 2 ui double prime, etc. Okay, now you take those and just plug them back into the formula, into the discrete formula. So substitute these into this discrete equation. Okay. So what you get, indeed, you just take them and substitute them. And I'll start with that. So look at that first term, ui n plus 1 minus ui n. So ui n plus 1 minus ui n is delta t u dot. Over delta t, you get u dot, plus delta t c squared, delta t squared over 2 c squared u double prime, over delta t, right? And then dot, 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 a bunch of other terms. This is what happens when you do this. Indeed, you recover your advection equation. But now this is the truncation error in continuous form. And this is going to be very important. So listen to this. This discrete equation is the exact discrete representation of the following continuous PDE process. Okay? So this equation is actually solving this. The discrete equation is actually solving this guy. Okay? So when you look at this guy, let's rearrange terms. I'm going to put the time derivative on the left-hand side and move everything to the right-hand side. You get advection. Now this term, which is the same here, just moves it to the right-hand side. This term is what? It's negative diffusion. It's diffusion term with a negative coefficient in front of it. So diffusion is smart. It works with the second derivative. where there is high concentration, is going to decrease it, and then when there's low concentration, it's going to increase it. It's very smart. It looks at the slope and figures out the second derivative, adjusts the sign, and it increases where there's low concentration and decreases where there's high concentration. But it has to have a positive coefficient. The coefficient multiplying this one here is negative, because c squared is positive, delta t is positive. You have a negative coefficient in front of it. So it's going to do the opposite of what diffusion does. It's going to decrease low concentration and increase high concentration. And that's why you see that blow up going on, okay? And this means you have unbounded, unlimited growth because it's a negative diffusion process, okay, which is unphysical, really. That's why the FTCS scheme on advection is unconditionally unstable. It sheds light from this modified equation. We will come back to this modified equation later and show all the effects we see when we apply different schemes. Every scheme that you apply is not solving the original PDE you started with. It's solving a modified PDE with extra terms in it. That's why you see decay in your solution. That's why you see oscillations, because you're actually solving an equation with different terms in it. Okay? But that's what we have to live with, right? Okay. Now, intuitively, so this is the second way we're explaining this instability. The first one was we tried to advect a pulse. It created a negative value. It's not satisfactory. This one is a little more satisfactory. It tells you that that FTCS scheme is solving an equation with negative diffusion in it, which is a no-no, right? Third intuitive explanation for this, advection, at least in this case that we're dealing with, is trying to move information in one direction. So in our setup, it's moving things from left to right. So we have the signal. It needs to move it from the left to the right, okay? But the central scheme is trying to bring in information, because it's central. It's bringing information from I plus 1 and I minus 1. Whereas I should only bring information from I minus 1. It's trying to bring information from the future, and it doesn't exist because this is advection. There's like, I don't know what's going on next, right? So if you look at my diagram here, the central scheme is trying to bring information. If things are moving from left to right, this point should only depend on the past or on previous points. Sorry, this is the past, should depend on previous points. But the central scheme is bringing previous points and next points, which is like, I don't know, it's not going to work. A better scheme would be if we only rely on previous points. So instead of doing a central difference, we can do a one-sided difference. If we're moving from left to right, take information from the left. If you're moving from right to left, take information from the right. We call this upwinding. You take the upwind value. If the velocity is positive, you take the upwind value, which is left-sided difference. If the velocity is negative, you take the forward difference. In this case, if we take, because c is positive for our example, if we take a backward difference, so things are moving from left to right, if we take this backward difference to approximate the derivative, I predict that things are going to work for us. Okay, and that's called the upwind scheme. Okay, so let's consider it. Let's do it. 1D advection on a periodic domain with the FTUS scheme. U stands for upwind scheme. Okay, upwind differencing, or forward in time, upwind in space. So you can use a backward or forward derivative approximation depending on the direction of the velocity. We call that the upwind scheme. Once we go in 2 dimensions with a velocity field that varies in space, you have to do a if statement. If the velocity is going from left to right, then use backward difference. If the velocity is going from right to left, use a forward difference, right? So you have to upwind it. The word upwind takes care of using backward or forward difference, okay? So this is what our scheme will look like now. Instead of a central difference for the spatial derivative, we're going to use a one-sided difference, an upwinded difference. In this case, because c is constant everywhere, it's moving from left to right, that will be a backward difference. Okay, and our scheme will look like this. All right? So let's go ahead and Pythonify this. So we can work with the same code. I don't think we need to to create another example code. So we can work with the same code. This is our formula. All we need to change is that stencil operation. Okay? All we need to change is that stencil operation. So we already have, excuse me. So we already have, this is ui plus 1 minus ui minus 1, right? So over here, instead of ui plus 1, it's going to be ui. And we don't have delta t over 2 anymore, c delta t over 2 delta x, because this is a type stencil from 0, 0, and minus 1. Okay, so this would be ui minus 1. So if you look at this, so it would be ui minus 1. Okay, speed times delta t over delta x. Just this simple change. Okay, let's go back to the Gaussian. I'm going to go back to the Gaussian function. So I'll comment this guy out, and we'll go back to our Gaussian function. So again, 100 points, L equal 5, etc. Gaussian function with a centered at 1, with a standard deviation of 0.25. Oops. U0, 1, 0.20. Oops, sorry. Yeah, this one. Okay? So if things are correct this time, we should see that signal move. Okay? Move from left to right. Are we in sync? Okay. Let's go and execute this and do it for 10 seconds, let's say. Okay. It should have executed. It's pretty fast. Let's do the animation. All right. Okay. Whoa, it's put a huge the limits. Okay, so let's see. Oh, it's still making an issue. I did that mistake on purpose. All right, so let's see. Did I actually run this? U0. Hold on. Okay, minus c dt over delta x. Okay, and then t dot plot, sol minus 1. Okay, so indeed, this is still problematic. How about I reduce the time step size, Maher?
If using u values, you should be using un with the time advancement.
Oh, that's right, un. Oh, man. Thank you, yes. Yes, and that was the same problem with the previous case as well. The previous case should have just, let's do it with the previous case. That's a great catch, Maher. Thank you, yep. un. Okay, so I'm going to do it with the previous unconditionally unstable stencil. Sorry about that, because it should just blow up everywhere. Okay, now see. Look at that. Okay, so that's the unstable one. All the points, they go to infinity. It's easy to make mistakes. Okay, so now let's change our stencil. 1 to minus 1. I'm going to have to redo the entire lecture now. All right, let's see. Yay, look at that. It is advecting. Okay? But it's shrinking. And in your homework assignment, you're going to prove why it's shrinking with the modified equation analysis. But off the top of your head, what do you think the modified equation is going to look like with the upwind scheme? So it's going to have advection plus a diffusion term causing it to decay that way. Is that cool? Okay, so forward FTCS on advection is unconditionally unstable. FTUS on advection is stable so far, but it's diffusive. Okay, let's increase our time step a little bit. Joel, are we good? Okay, so let's bring our time step up. 1 order of magnitude, so 0.1 second. Okay, I'm going to run it. Let's see. Oh, it blew up again. Well, at least we got a stable solution for some time step value, right? Okay, let's maybe go to somewhere in the middle, 0.05. Okay, let's see. Oh, look at that. It shrunk just a little bit, but it's stable. Okay. So I want everyone to be in sync now because we're going to get back to the lecture. If you need any help, raise your hand. Oh, big crash over here. Yeah, so your solution needs to be from 1 to -1 here. Because we created, we created an array of n plus 2, right? So you're going to slice it to n points. Because x is n points, yep. So 1 semicolon -1. Okay, so try now. Oh, there you go. Yay, awesome. Okay. Victory. Okay. So while you guys were trying to figure that out, we tried different time steps. And there was a time step value where it became unstable again. But at least there were some time step values that it was stable. Just like we saw with the diffusion. And with diffusion, the condition was that the Fourier number needed to be less than half. There's another condition for the FTUS scheme, okay? So let's go back to our slides and see if I can move this over here. Should we do it together or leave it as a homework assignment? What do you think, Maher?
Let's make it a homework assignment.
Let's make it a homework assignment. That's what I was thinking. So in your homework assignment, you will deduce why this pulse is diffusing with FTUS scheme, okay? And you will deduce a condition on the time step size. You will essentially derive the CFL condition using that pulse idea. It's going to be a condition on the Courant number. And there's a little mystery over there that you can challenge others with it and tell them that you can actually get the exact solution numerically only for one-dimensional upwinding by choosing the correct value of the Courant number in the right time step. So that'll be in your homework assignment, okay? So I'm going to skip those slides here. So in your homework assignment, you'll derive a condition on the Courant number, okay? And you will derive a modified equation to explain why that pulse diffuses. And you will have to show that there's going to be a diffusion term, okay? Okay. Are we ready for the advection diffusion equation? We did diffusion, we did advection. What the heck, we can do advection diffusion, right? Do we have, maybe we have 15 minutes. Shouldn't take that long, okay? So let's do it. This is the advection diffusion equation. We're just adding advection and diffusion, okay? Pardon me? It's unsteady, yeah. Okay, so forget the exact solution for a second. Well, okay. We will eventually need to work with an exact solution, and I'm showing here an exact solution to the advection equation, to the advection diffusion equation. If your initial condition is a sine omega x, then an exact solution for that equation is a sine omega x minus ct e to the minus mu omega squared t. If you think about this, this is the advection part that's moving that signal, and this is the diffusion part that is diffusing it. Okay? Advection, diffusion. Advection, diffusion. Okay? Anyway, we'll worry about that once we get to doing some error analysis. I'm going to propose the following numerical scheme. And I'm going to use forward in time for the time derivative, central in space for diffusion. Okay? I'm going to use central in space for advection. What the heck? Didn't we just prove it was unconditionally unstable? Why would I choose it here? Can you explain why? Could this even work? Recall that we just showed that FTCS on advection is unconditionally unstable. but on advection only. Can you explain why this might work? Yes. And in your homework, and what we showed last time in class, that diffusion is very good with high frequency waves. So anytime the central scheme, FTCS, is going to cause some unboundedness on advection, diffusion is going to squash it, right? And that's why you can get away with central on diffusion, we will show that, on advection, because you have a diffusion term. But it needs to be the right balance. And again, there's going to be a condition on the time step size for both the advection and diffusion term. And it's going to be incredibly more complex. Okay, but first, let's just get our hands dirty. And we Pythonify this. Okay, let's go ahead and Pythonify it. All right. For this one, I'm going to create a new notebook. So let's create a new notebook. And I have to change. I have like a bunch of untitles in every folder, like untitled 50. And I'm like, so I should call them in class. Okay, linear advection diffusion equation. Equation with FTCS scheme. Okay. No. This is not the new notebook. This is the old notebook. This is linear. This one is the linear advection equation with FTCS or FTUS scheme. FTUS schemes. Okay. So let me get my new notebook from here. Window. And this one, untitled 2, is going to be in class linear advection diffusion equation with FTCS scheme on both. So central on both, FTCS central on both advection and diffusion. Okay? All right, let's grab our boilerplate from another, In fact, we could just duplicate, you know what, let's just duplicate this one. Actually, it'll be easier. Just duplicate this notebook, the other notebook that we just finished. So just duplicate this one. If you go make a copy, okay, and then, all right, 1D linear advection diffusion equation with FTCS scheme. Okay, so this one is going to be, we're going to have to add one more term here. That will be plus mu delta t over delta x squared, right, times the diffusion term, or the second derivative approximation, which is minus 2 ui n plus, right? So c dt over 2 delta x plus mu delta t over delta x squared. So that's what we are implementing. Okay, and we should be ready to hit this and just make it work. So it's going to advect and diffuse at the same time. Okay, again, I will keep my Gaussian. Same thing here, my Gaussian. And we'll keep the settings here as they are. And for simplicity, I'm going to define now, I'm going to call C delta t over delta x, I will call it the Courant number, CR. And this one is the Fourier number, mu delta t over delta x squared. So once I determine delta t and the wave speed, I will define my Courant number. Courant number. Let's see, R equals C times dt over dx. And the Fourier number is mu times delta t over delta x squared. Okay? Nothing has changed here. Wave speed, 1 meter per second. Everything is the same. Nothing changed, except here. Okay. So now I have the Courant number over 2, multiplying the centered scheme on advection, okay, plus the Fourier number times what was the diffusion stencil. You can grab it from the previous from your previous notebook, or just simply set it up here. You have ui plus 1 minus 2 times ui, which is 1 to minus 1. Oops. And then plus ui minus 1. Advection is central. Diffusion is central. Yes?
Sorry, I couldn't type this fast.
Oh, what are you at?
I got lost back at the 48 number.
Yes, okay, yeah. So to simplify, rather than keeping like delta t and delta x, etc., once I define delta t and the speed, I'm going to define my Courant number and my Fourier number. And this is periodic, okay? So what do we expect? We expect things to advect and diffuse naturally. There might be more diffusion coming from just the nature of the schemes themselves. And we don't expect this to work for all time steps, right? Because we know there's a limit on stability, because individually, the central scheme on advection is unconditionally unstable. The central scheme on diffusion is stable up to Fourier numbers less than half. Combined together, the stability condition, which I will discuss next, is going to be different. It's going to be a combination for both Courant and Fourier numbers. And so, it might work for this time step, it might not. And I'm doing this choice on time step on purpose because that's the only thing that we've been in the dark about. So we have no guidance on it yet, right? So let's see what happens for this one. We run it for, let's say, just 2 seconds. Yes?
I was already good to see what the while
Yeah. Yeah, so for the while loop, then we update this to Courant over 2 because this is central on advection, right? You have over 2 delta x because you have I plus 1 and I minus 1. So the distance between them is 2 delta x. If you're here, just run this and run the animation. Let's see what happens. Oh. Here. Anyone has it running? Reduce the time step size. So go 1 order of magnitude less. Let's see what happens. Again, we're still shooting in the dark. We don't know how to choose this. We still need to define the mu, which we didn't define, right? So we'll define mu somewhere here, maybe. Just set mu diffusion coefficient, maybe 0.01. OK. Did we get this typed up? OK. So you should run it. It should run. And let's see the animation. OK. OK, it's blowing up. Or it's going to blow up soon. So look at that. It's creating negative values on physical. So I expected this because my time step size was chosen just arbitrarily. Let's go 0.01. See what happens. Maybe it's better. Oh, yay. Look at that. OK. So let's run it for longer time. Let's run it for 10 seconds, perhaps. Oops. 10 seconds. OK. So it keeps going and go. But look at that. It has a little kink over here. So it's going to go unstable at some point. Right? You see that negative kink over here? OK, so I'm going to keep going, keep going. You see that little kink over here? And we're just like borderline on the stability. Okay? We're still shooting in the dark, and I never claimed otherwise, right? Okay. So now, maybe we implement our analytical solution for the diffusion equation, advection diffusion, and see if we can at least get close to that. Okay? So from my slides, let me grab them here. We had this analytical solution. Initial condition A sine omega x, and then the exact solution was A sine omega x minus ct e to the minus mu omega squared t. Okay, so here's what I will do. I will implement simply a u exact, another u0, and I'm going to give it a lambda. This is going to be x, omega, and t. Okay, and I will do a is equal to 1, so amplitude is 1. So we will do mp dot sine, p dot sine, omega x, okay, times mp dot exponential minus mu times omega times t. Okay, so this is going to take mu, and we'll make mu as a global variable. Okay, so we don't have to pass a ton of arguments every time. Or you can make it mu over here, okay? We're kind of running out of time, but at least I can show you this one. So let me comment these out. So this is analytical solution for advection, analytical solution for advection diffusion equation, okay? So at 0, my initial condition is going to be at t equals 0, right? So I'm going to call u0 at x, omega, we'll specify omega equal 2 over here, let's say, and mu is equal 0.01. So x, omega, 0, t equals 0, and mu. This is terrible. I should put x and t at the end. X and t, okay. So we will do omega, mu, for all x and t equals 0, and then I'll plot it. X and then u0. And this is my initial condition. Okay, so what I expect for this is to advect and decay. Okay, as you see in my slides, this is the analytical solution. It's going to advect and decay. So we're going to compare our numerical solution just from the initial condition, right? So we're just going to set the initial condition, and interestingly enough, that PDE is going to figure out how to evolve it very close to the analytical solution. We'll see. There's going to be an error. Okay, we can explore that, I think, next week on Thursday if you want. Yeah, we can explore that on Thursday. Let's see if maybe I can run it over here. Okay. Yeah, I would need to create an animation for the analytical solution, but let's see at least the animation for the numerical solution. I'm going to comment this out. It's going to it's doing something weird with periodicity. Okay, so we'll fix that next time. All right, we'll fix that next time. And at least we got to do some advection diffusion. So on Thursday, we'll get to do this with the analytical solution. We'll compare to the analytical solution, and we'll dig into some conditions on convergence, consistency, and stability. And there's a very nice theorem that tells you about convergence of numerical methods, because all of these things we've been seeing, stability and time step size, etc., they're all tied in together to three things called convergence, consistency, and stability. The three of them, two of them imply the third always. And so we will talk about that on Thursday, and hopefully we can do a 2D example